Yeah, so welcome everybody to the weekly seminar of our group. Today, our speaker is Ondřej Hulík, who's going to tell us about his latest work on extended geometries in string and M theory.
Okay, thank you for the introduction and invitation. Hopefully, so this is just to make sure you see again the screen and hear me well, right? It's all
yes.
fine. Yeah, cool. Okay. So yeah, this is sort of gentle introduction.
Ondřej, I don't hear you.
What about now? Is it better?
Yes.
Okay. Yeah. Okay. Sorry about that. It's my headset. It always does something. So yeah, as I was saying, this should be sort of as a gentle introduction to string and M theory and sort of highlighting these extended geometries behind the theory, and it should sort of work as a build up to next week's talk of Friedrich, who's gonna talk about our most recent paper with Mark, who's sitting here also, and Dan Waldron. But I figured I'm gonna go over some basics, hopefully not too basic things, and some people will still get something out of it. Yeah, so feel free to interrupt if there's something unclear, or if you want to add something. Maybe I'm not saying the right stuff. So I'm okay with being stopped and corrected. So right. So with that said, I have these three things I want to mention so that you see the work we did sort of in broader picture, and why would we be interested in objects which Friedrich will be talking about next time. And so I want to yeah, there's really three parts of this talk. I'm gonna tell you how sort of extended objects in physics see richer geometries rather than just Riemannian geometry in the particle setup. So string theory is sort of naturally formulated in a language of generalized geometry, or even more generally in the language of double field theory. And for branes, there's exceptional generalized geometry. That's the egg here, and the analogously for DFT, there's exceptional field theory here. I won't get to that, but that's just the underlying picture. And then I'll mention briefly how these extended objects also yield a new feature which haven't been seen in particle setup, and that's the D and U duality, which is some non-trivial duality of the model, which preserves the spectrum, but it non-trivially acts on the geometry, and I'll say a little bit about that, and then last thing I'm gonna talk about is these were just the tropes of the space, but upon second quantization and looking at the target space effective field theory, we have these theories of gravity and supergravity and M theory for branes, and they also sort of inherit this extended geometry as a underlying framework. So that's what I'm going to talk about. Let's move to the first slide. Unless there's any question, I should probably ask that from time to time and slow myself down. So if that's not the case, then I'll start it. As I said, we do like in physics to probe the space with different objects, and the most general the most basic thing you want to have to be propagating in your space is particle. So there was long history of quantizing particles and looking at the effective field theories in the target space, and it's usually, you know, it's really described by nicely within this Riemannian geometric framework. And I also wrote down this GLD group behind, which will be the G structure of the principal bundle of the manifold, and along these lines, there's these generalizations. Strings sort of see more general geometry as generalized geometry, and membranes see the exceptional geometry, and there are these extensions of the structure group to ODD and EDD. Sorry, ED. This is not this is the split form.
I don't hear you.
Can you hear me now?
Yes.
Okay. Okay. I'm sorry about that. I don't know what's going on. I just unplugged my headset and I'm just gonna talk to my tablet. Hopefully that's still okay quality. So yeah, so particles, we sort of know that they couple naturally. You know, when you write down the Polyakov action, they couple naturally to the metric, to the background metric, but there's also electric coupling to gauge field, right? That's something we know from mechanics. We can take one form from target space and pull it back to world line, and that's a natural electric coupling of one form. And so there's these underlying pseudo symmetries. I don't want to call them symmetries because they sort of shift us in the space of couplings, because we, you know, the given G and A, it provides some background for world line theory, and if we act on our world line action with diffeomorphisms, we move to another background. So it's more of a like what's it called, deformation of the model rather than the symmetry. But there's also this other symmetry we usually not think about, that's adding to the action D of 0 form, which changes the gauge of the one form, and it's also a pseudo symmetry in a sense. It changes the gauge field in some way. For strings, there's something similar happening, and already you see this generalized tension bundle emerging. That if you look at the pseudo symmetries of the string model, there's a natural coupling to G. The metric again, that's the same, and there's a coupling to B field, which is the higher dimensional analog of the one form. So you can pull back two form to two-dimensional object and integrate over, and there's these pseudo symmetries. If you analyze them, you get the vector again, and you also get the one form here. So that's something naturally living in space like this. Well, maybe I should change the color here, so that it's clear. Okay, right, like that. So it's something living in this space instead of just the M. And for p-branes, yeah, you get the point here. You have a p-dimensional object living in the space, and a natural thing to couple along with the metric is the p form. So you can pull back the p form, and there will be a this space underlying the pseudo symmetries, and that's the space of p forms plus vectors. So from the world volume perspective, for different extended objects, we see this extended tangent space emerging as a natural space of pseudo symmetries, and so that's, yeah. Let me just spell out some details in the most, you know, well-studied example, and that is string theory and how it's how it's intimately related to generalized geometry. So the string model, as I said, it naturally couples to G and B. Well, I call them capital G and capital B before. Is there any question maybe before I go further? No. Okay. So this sigma model is something like this, right? It couples to G and B naturally. It's a two-dimensional sigma model, so it maps worldsheet into target space. Maybe here, forget about this for a moment. Then there's a as I said, the symmetries are naturally living in Tm plus T star m, but also another feature where we sort of see that there's this underlying generalized geometry playing important role is when we study its Hamiltonian description, and that you all probably know that the way we do that is to identifying canonical momenta, and then when we construct this Hamiltonian, we see that these objects. So we not only have forms, but we also have the x primes, right? These are like x dots, and these are x primes, and they all together they. There's someone talking. Is there a question, or is that just echo from somewhere? No. Okay. Okay. Right. Or is it me? Is there echo coming from my? Can you all hear me well, or not?
There is a very slight echo.
But now it's good, right?
Okay. Okay. Cool. Thank you. Thank you. Okay. So right. So there's this way to. So if you write down the Hamiltonian, there's this natural object emerging, and that's another evidence for generalized geometry that Hamiltonian just is expressed nicely. Well, it's an inconvenient choice of letters. This is Hamiltonian, and this is so-called generalized metric, which is something we will be naturally written in terms of the geometry of the generalized geometry. So as I said, these are naturally again living in TMT star m, and this is some new object which plays a role later on. Right. So there's this new feature I was just gonna glance over because Friedrich will probably have something to say about T dualities and U dualities. In string theory, we know that on the toroidal background we notice that upon quantization we get this interesting spectrum which consists of momentum modes and winding modes, and we see that. So this is in particular for target being SR, which is circle of radius R. So we notice that these two terms are actually quite similar, and if we were on the circle of 1/r radius rather than R, and switched what the momenta and winding means, then the spectrum would be invariant. So this was the first evidence for some underlying symmetry, which is apparent at the level of spectrum here, but it also has some geometric meaning. And the geometric meaning was first sort of made more clear at the level of geometry by Boucher, and the thing here is that I was at the circle with the isometry being U1. I know that this is a general, this is a natural generalization. If I have toroidal background and I have some isometries of my background, so if I'm on Tn, there's these U1s acting to the n acting on this. If these are the symmetries, I can gauge these. I can introduce gauge field for each of these. And I gauge the model. I'll add the gauge fixing term, some x dot, which upon varying tells me that f is 0. So and then I can write down this parent action. So parent action is something where the gauge field is along with the original coordinates and the dual coordinates, which are the gauge fixing Lagrange multipliers. Sorry, maybe not gauge fixing. Yeah, Lagrange multipliers is a better word for it. So if I integrate out its x tilde, I find out that f is of pure gauge, and I can write as d of x and subsume it in the x and get the old action. It turns out that if I do something else, if I integrate out x instead, I can pass to a dual model here and find dual action. In particular for S1 background, what I was introducing on the previous slide, what actually happens is that if this model was, in the geometry of circle with radius r, this one will be on circle of radius 1/r, and for more general geometries, we get these so-called Busher rules, which I spelled out a bunch of them. It's really some nonlinear transformation of G's and B's. Okay, maybe red is better. G's and B's of the original model being transformed to some G tilde and B tilde of the dual model. And if you look at the quantum theory, if possible, then the spectrum is the same. So that's the. However, it's not some trivial transformation, as you see up here. I spelled out, for instance, how under T duality in the 25th direction, what happens with G 25/25. It's some terrible mess, but interestingly enough, it's still, if this was a solution of supergravity, this will be as well, and it has its nice reformulation in terms of the generalized metric. The generalized metric was a function of G and B, and if you perform this duality, it will yield some new generalized metric, which is really connected to this guy by some conjugation with some with some group elements, but I'll talk about it more later. And there's all these generalization. I don't have to talk about it, but yeah, that's pretty much it about the world volume, world G, and world line model I wanted to say. So there's this new duality. It also appears in the membrane models, even though it's not that straightforward and less studied. And so we noticed that there's some bundles with some forms in appearing here, and they play a role in extended objects. And we also noticed in particular in string theory that there's this T duality, which hasn't been seen in the particle setup. And now I'm gonna switch gears and talk about the target space effective theory. So what happens is that in physics we like to first probe the space with strings, say, and then when we look at what are the excitations created by string, we construct this target space action called Stringfield Theory, and which has all the, probably you know that Stringfield Theory is super complicated. It has all these higher massive modes of higher spins, and we really just keep this underlying massless subsector, which is the supergravity. And so obviously if we've seen these interesting structures somehow already at the level of the world sheet model, we should expect that they will play a role in supergravity, and indeed that's the case. And for M theory, this line of thoughts of going to SFT and then supergravity, that's to this day unknown. What is this full SFT analog of the fully quantum second quantized M2 and MFI branes. So we only know this low energy M theory action, right? So as I was saying, there were these three things occurring which were interesting and different from normal geometries, and that's the pseudo symmetries, dualities, extended space I didn't talk about. Right. So right.
Can I ask a silly question?
Yes.
in these diagrams, isn't it better to put also sugra at the end of the second row? I would rather call M theory like the whole second line. I don't know if that makes sense.
I don't understand. What do you mean?
Like the question mark in the second slot and in the third slot sugra again, like a different sugra.
Oh, sorry. Yeah. I guess sorry. So yeah, this is more like, yeah, this is 11-dimensional supergravity, I guess. Right. Yeah. Sorry. Yeah. I got confused. And this is whatever this is. It's still a question mark, but I guess that's what we call M theory, really.
Yeah, maybe. Okay. Yeah.
Yeah.
Just sorry for silly.
No. That's right. No. I guess I haven't been thinking about this question mark forever, and I guess I just eternalized this being M theory, which it's not. It's massless limit, and we don't really know what the M theory is. Sorry about that. Thank you. Right. So supergravity in 10D, which is the critical dimension of string. Now it has these fields. We've seen part of them, this G and B, because they naturally couple to RNS string worldsheet model. But there's and indeed so there's more of them. There's these RR forms you might know, and maybe you don't think about them that much because they really need a different formulation when you see them from the worldsheet perspective. But yeah, they all form this bosonic field content of the 10D supergravity. You might know that there's 2A and 2B 2A and 2B models. In the bosonic sector, it just differs by what this RR forms are. They naturally we'll look at that later, but they live in different representations of this ODD group. And there's this so we've seen the part of the I said that the G and B are somehow transformed by these TM and T star M generalized vectors. So the psi I they generate the diffeomorphisms, and then there are these one forms which are the gauge transformations of the B field. There's all these R forms, and you can expect that there will be extra bit, and indeed there's extra bit which are higher forms, and I'll talk about them more later. In M theory, all this terrible bosonic sector of the theory recombines into rather simple spectrum, and that's the metric 3 form and 6 form, and then the underlying bundle of symmetries is now something you can guess, from the previous. So we had 2 form, and there's 1 form gauge fields here, and the diffeomorphisms they stay. So diffeomorphisms are indeed in TM, and then we have these gauge transformations for C3 and C6. So they are the 2 forms and 5 forms. If we take these of them, we can add them to C3 and C6. It gets a little more complicated in lower dimensions. There's some KK modes appearing from dualizing dimensionally reduced graviton, and there will be extra bits, but there's simply no time. Not that I fully understand all the pieces of it, so it's a good excuse for me to skip that. Right. Is this clear? This was lightning review of the bosonic spectrum of I guess I called it M theory here again, not being consistent of that 11-dimensional massless limit of M theory. Right. So is this clear? Is there any question, or should I proceed? Okay, so I'll go on and right. So I was just gonna make a little digression here about G structures, which is probably something you all know better than me, and just pointing out that there was this TM over M in Riemannian geometry and natural underlying the theory of particles and the usual GR. And TMT star M over M is the stringy and sugra setup. and we can sort of see these as associated bundles of some different structure groups, and that's what will sort of play a role later. Because once you accept this, you can just switch structure groups and study whatever are the exceptional geometries for different structure groups. So for instance, yeah, right, this is just something associated to GLN. This is fundamental representation associated to GLN vibration. Here it's the ONN, and it's fundamental here. If we add this S plus here, as I alluded to earlier, or S minus, this was the extra bit here. We're also at some. We'll associate more representations of ONN, but I'll say more about it later. Okay, and there's also this analogy goes further. We can what we know from normal geometry. If we want to get metric, the natural thing is to reduce structure group from GLN to maximal compact, which is SON, and this moduli space GL over SO, it gives us the all the metrics in every point, and there's an analogous setup here where we if we start with ODD, we can find this maximal compact under it, OD times OD, and indeed if we look at this, so this should be analogous to the metric of the Riemannian geometry, and that's exactly this generalized metric we've seen in that Hamiltonian. So it all fits nicely, and all the other objects we know from geometry, like the Lie bracket and exterior derivative connection, sort of translates with some caveats which are more or less important into generalized geometry. So and with this set, the exceptional geometry will be the same thing where the structure group will be this EN, this arcane exceptional group EN. Right. So is this, yeah, there was probably no question about that, right? That was very schematic, but yeah, so just to give you a little, you know, little closer information about ODD. So that's the supergravity setup for string. So ODD is a split form of 2D. It's this this Dinkin diagram, right? And if we look at this Lie algebra, these generators of this group with respect to the split form, this is the one I'm choosing for ONN ODD. Sorry. Then it has this block diagonal form, and we identify these main diagonal guys as being unrestricted. So there's this GLD bit, that's the little a, and there's these beta and B guys, and they are anti-symmetric. So so there is this nice decomposition. There's this GLD bit under and we can, it is customary and very often useful thing to decompose this ODD under GLD sitting inside and its representations. So under that, I'm gonna write it like this. Especially, to NT star. So especially will come in handy when looking at the EDD group. So right, so this is the ODD with the GLD inside, and this GLD is the right geometric subgroup, so-called, meaning that if we look at this fundamental representation of ODD, it splits under GLD into T and T star, which are the fundamentals of GLD, and they will really, you know, upon associating to that principal bundle, they will really play the role of Tm plus T star M, and GLD will just act on them, you know, as you would expect. There will be exactly those size, you know, the diffeomorphisms transforming the vectors and forms as you would all do. But there are these non-geometric parts which sort of intertwine these two elements. You know, if we could have associated this Tm plus T star M to GLD principal bundle, but they wouldn't be connected in any way. They would be just two two representations sitting there as a direct product. But here we have this bigger group which sort of intertwines them, and it does so via these two parts. So this guy is two form, right? And two form can eat a form and send it to vectors. So it acts this way, and likewise the two vector. Sorry, I got it the other way around. This is two vector, so it takes a two vector. So it takes form and send it to vectors, and two form takes vectors to one forms, right? Okay. So that's that. There's also the H appearing, which was the generalized metric, and it squares to 1. That's an extra constraint, and it's really an element of this ON n over ON times ON, which is an extra reduction. You see that, this is maybe worth noting also, that a priori maybe you would expect something, without any structure on your manifold. You would expect a group of GL, GL2D perhaps, but we already have sort of reduction, and that reduction is given by this natural pairing I've introduced, because there is this canonical way to make a number out of T star m, and that's by contracting, putting that vector into one form and producing numbers. So that's already some rigid geometric structure which gives you that ODD group, and then you can do further reduction to get the generalized metric. Okay, right.
So sorry, can I ask a question?
Yes.
So N and D, they are the same.
N and D.
There is ONN and there is ODD.
Oh, I'm sorry. Yeah. That's
okay?
just me being. Yeah. Sorry.
And what do you mean by H squares to 1? Like what should I understand as H?
Oh, H. Sorry. Yeah. Okay. So H is really some endomorphism of the TMT star m.
Okay. Thank you.
So yeah. Sorry. Maybe that's not that usual of a notation. What I mean by H is this endomorphism, and then if I want to make a metric out of it, I would put it in the pairing and produce a. Maybe some people might call that H, but yeah, I guess that's then it wouldn't make sense. Sorry about that. Yeah, and N is D. N is D. Is there anything else at this point, or no? If not, then I'll continue. And so there's also an extension of a bracket. So there was a natural bracket for GLN structure, and there was the Lie bracket, right? The Lie bracket we all know and love. That's this UNV, and it's I'll just spell it out because it's useful for later. There are these two terms which will play a role later. Sorry. So there's this usual directional derivative, and then there is another term which looks like this. And yeah, we have this in GLN geometry. In ODD, we have a natural generalization of this, and that's the Dorfman bracket and Courant bracket. Maybe Friedrich would be unhappy now that I'm saying that it's natural, the Courant, because Dorfman is probably more natural, but they are, I guess, they both play a role in different situations. So and the way to sort of write them nicely in and see them how they come with those two structures is by exploiting this formula, and this second guy, it really it takes a vector and outputs this GLN transformation. So this is GLN Jacobian, right, of the infinitesimal diffeomorphism. We can, so if we're in the ODD structure, we can do a similar thing. We can take those vectors and forms, we can put them together, and we'll get a priori something in GL2n here in this Jacobian part of the Lie bracket. And then ODD sits inside GL. I'm saying D and then GLN. So yeah, D is N again. So GL2D and there's ODD sitting inside. So the simplest thing to produce the Dorfman bracket is just to project down to ODD. So we do that and we get this different bracket, this D bracket, and maybe also Lie derivative with D superscript. And but by doing this projection, we screw up a few things. So we no longer have anti-symmetric bracket. What's nice is that the Dorfman bracket is still it still satisfies Jacobi identity, but it's no longer anti-symmetric. We can, although yeah, sometimes it's useful to, as I was saying, there's two brackets really. Sometimes it's useful to have really anti-symmetric brackets, so we can anti-symmetrize by hand, by brute force. But then we produce something anti-symmetric that's called Courant bracket, Courant. But as it happens, it will not satisfy Jacobi identity. So there's this, yeah, there's this. Duality here. Either you use Dorfman or Courant, and you have to sacrifice one of the things, Jacobi or antisymmetry. Right. Right. So that's the bracket. There's a natural, and again, I said this for a reason, because as you can imagine, in these higher geometries, there's always this underlying structure group, and so every time you'll come across this higher geometry, natural thing you can do, you can take the second term, you can project to some subgroup which will be matching that structure group of your vibration, and off you get a new bracket, and you can study that. Sometimes, yeah, sometimes it will be even worse than Dorfman and Courant, but yeah, that's something you can certainly do for extended bundles. Right. Right. So yeah, I was also yeah, a little warning here is that even though it's usually written TM plus T star M for generalized, it's not really that. It's that only locally, meaning that only over a neighborhood U, it's TM plus T star M. But between different neighborhoods, you can actually mess up, and you wouldn't be just identifying vectors with vectors and forms with forms, but you might find that there's this twist of this generalized tension bundle, which will also add this two form, and you can sneak in X inside and produce a form. So there will be some combining of the vectors and forms together when passing from patch to patch. So it's not really it's not really a direct sum globally. Yeah, but maybe I'm not gonna talk about that more. I'm gonna switch now to M theory, and as I said, so ODD was for generalized geometry, and now we have this EN group, and that's what is underlying M theory. So they you know that you can get you can get a 10-dimensional supergravity from M theory, or 11-dimensional supergravity by dimensional reduction, by putting it on circle and just taking the lowest modes. And this is hidden at the level of that structure group. It's hidden in the fact that this ODD of generalized geometry sort of fits nicely into ED group. So EDs look like this. They are not just fork, the symmetric fork like OD, but they have this extra extension, and that's exactly that extra node you're adding. If you chop it off, it's as if you did that reduction and outpops the ODD with extra stuff. So ED, yeah, ED is that's the reason why ED sort of naturally appears in that one step higher, in one dimensional higher, and that's because that's something where OD naturally sits. I'm not writing here. There's also, this is a real form, so this needs to be a real form, and usually it's written like this or with the bracket, and everything sort of recombines into something bigger in M theory. So T duality was duality of those strings. It recombines with the S duality into U duality here in M theory. The NS and R sector of the string, those B's and G's and R forms, they recombine into just a metric and 3 form and 6 form in M theory. So that's, there's a lot of unification happening. So right. I was right. So yeah, as I was saying, there are these S's, those extra bits which are the gauge transformations of RR forms, but they happen to all recombine into exceptional manifold like this, and indeed, we'll see in a little bit how these different parts of exceptional group intertwine these different parts. Let me just say one more thing, is that this whole thing is a representation of ODD, and this S plus happens to be also a representation of ODD, and or S minus in 2A and 2B setup. And what they really are, they are spinorial representations of ODD. So spinorial representations of ODD, they happen to be really just all the forms of that space T, which was the fundamental of GLD. And these are not irreducible. They decompose into under parity. They decompose under into even and odd forms, and those are the S plus and S minus. So this right tangent bundle for 2A and 2B, it's really Tm plus T star M, and extra stuff from the spinorial representation. So it's fundamental plus spinorial. There could be extra bits actually. I'm not saying all the stuff which are coming from the charges of NS5 branes. Right. But all of these TM, T star M, those NS5, NS plus, S minus, they recombine into this. So what I mean by recombine is that if I reduce this guy, this huge exceptional tangent bundle to S1, I'll be getting just to give you a flavor of it. If I have 2 form, I can imagine just I'll write it here maybe. If I have 2 form, I can imagine that it either gives me a 1 form in 10D. So this is 11-dimensional 2 form. So if I single out this, say 11 direction, it will give me 1 form. Or if I keep all the indices within my 10-dimensional space, I get the 2 form down in 2D and 10D. And likewise for these guys. And yeah, it's not that simple to do it in short time, but you can pretty much reconstruct everything up here. Right. Right. So that's what I said. So yeah. So maybe these geometries are maybe a little arcane with the ED, and that's why people focus on lower dimensional geometries and as examples, because you can sort of think of if I take this series of E's, I can start chopping off this from this side, and that's going down in dimensions. So I started with E8, right? That the highest of E's. Well, you can have higher, but they're not finite dimensional algebras. So that's what 1, 2, 3, 4, 1, 2, 4, 5, 6, 7, 8. Well, I got it right here. Okay, and then when I start chopping off those guys, I get E7, E6, and then I can naturally continue, right? And but when I chop off this guy and go from E6 down to whatever should be E5, I identify with the spin 5-5, right? Or with 055 here. And then I can go further, so I can chop off an extra bullet here and get SL5 if I straighten up this guy, and then I can chop off this, and I get SL2, sorry, SL3, SL2, and so on. So that, yeah. So sometimes it's useful when you don't want to, you know, study all the exceptional group representation theory, to just start down here and study examples in lower dimensions, and just work with your usual nice groups you know better. Right. Right. So right, but if you go in these higher dimensions and start having these real bona fide exceptional groups, you actually, that the life is not that hard if you remember what we did for ODD or ONN. I guess they are the same again. We decompose under this GLN, and that's a common feature for these geometries. There's always this GLN underlying it, and that's your geometric subgroup, which is playing a role of you know, of what are the, you know, what was the normal GLN, sorry, was the normal GLN over M in the principal vibration. So all these extra bits, you should think of them as sort of extension of this vanilla geometry with GLN. So you can do different extensions. You can instead of having this GLN with two forms and two vectors, you can do different extensions. And if you look at what is the what is happening for EN, if you decompose it under GLN within, you find that it has a similar structure. It's not just that it has two forms and two vectors in it, but it has three forms, three vectors, and six forms and six vectors. So that's how it's sometimes useful to think of these EN groups when you're in higher dimensions, and even in lower dimensions per se. So that's something I wanted to mention. It might be useful for what Friedrich is talking about. And now, yeah, I'm almost heading towards the end of what I was gonna say. I wanna just give you a simple example of how this geometry of this line looks like, this four-dimensional geometry with SL5. And so yeah, so SL5 geometry, it has this four-dimensional tangent space, and if you calculate what the second wedge power of the D star is, it's six-dimensional. So if you put them together, this will be your exceptional tangent space, and it's Tm plus wedge to T star M. If you sum up 4 and 6, you get 10 dimensions. So this will be your exceptional tangent space. And as I said before, there's this GL4 within within the E5, E4, and it acts on these individual guys separately. So that's the geometric subgroup. It acts on Tm and which the T star M separately. But then there's these extra bits. There's these three guys. There's not 6 ones because we're in low enough dimension, and they do what was happening in the exception in the generalized geometry. They intertwine these two independent elements under GL4. So 3 form takes a vector and eats it and produces 2 form, and it works the other way around by sending the 2 form into vectors, right? So if you see it, although so this was a decomposition of GL4, so GL4 plus wedge 3 5 wedge 3 D dual 5 4, sorry, 4 as in the dimension of the representation of GL4. You can put them together into SL5, which seems to be the right dimension because you know, this is GL4. That's 16, right? Plus 4 plus 4, so that's 24. That fits. And the this guy is 10-dimensional, and I was claiming that it needs to be in representation of SL5, and there is indeed 10-dimensional representation of SL5. There are 2 of them, but this one happens to be, if you work it out, it happens to be second wedge power of the fundamental. So this space seen as a associated bundle to SL5 is just what you would get from associating this wedge to R5. Right. Right. So there was this pairing also in the generalized geometry, which was having those one forms eat vectors and produce number. Here's something similar, but slightly more complicated. I guess Friedrich will talk about it also, so I'm not going to say much, but yeah, there is this way to mimic the pairing from ODD, and they will play a crucial role. And it's really similar here. It just you feed those vectors into 2 forms and produce a 1 form. So there's mapping into this other associated bundle of the SL5. But yeah, since it's not really a pairing, this is non-trivial representation. It will complicate some things, but nevertheless, it can be worked out and given some meaning. But okay, so yeah, that's yeah. I think I'm nearing. Well, I'm at the end. I was gonna sort of flesh out this example and give you some introduction how these objects appear in supergravity, and if you wanna see how we sort of worked out this unifying formalism, how to see these algebroids, these exceptional tangent bundles with their bracket in a sort of a unified framework, meaning that generalized geometry and exceptional geometry fit into one neat definition. Stay tuned for Friedrich's talk next week, and thank you for your attention. And yeah, if you have any questions, yeah, feel free to ask. And otherwise, thank you.
Thank you. Yeah, very nice review of exceptional and generalized geometry. Thank you. Are there questions?
I said that Friedrich will talk about many things. Hopefully he was really meaning to do that. I wasn't just now pushing him to say something what he doesn't want to spend his time on.
Yeah, maybe I have a comment on what you said about the global identification of the stuff with T plus T star.
Mm-hmm.
You were saying that this is true locally. So I guess it may be slightly better to say that it's true that locally you can always make it in a form there is no H, like it's really just this simple Druckmann bracket. But for courant algebra it is possible always to globally have at least in the real category, or like the smooth category, you can always make it globally T plus T star for the price of having some 3-form flux, some twist in the bracket. But at least like T plus T star, you can always make it globally. For the exceptional case, I'm not sure, or I mean, I at least I don't know. I don't know if the corresponding statement is true there. So
Right.
Yeah. But yeah, thanks for the nice talk.
I think it's worth saying that we expect it to be true at least up until certain dimensions. Like for instance, for the E3 and E4, it's almost certainly true that it's this form at the expense of a closed 4 form.
Maybe I have a question. So these, like in relation to the string theory, this is let's say kinematics. This is the field content, right? And what you are describing is the field content of the theory.
It's more like a,
or can you say something
gauge,
about the dynamics, or how does
I
it?
guess it's the gauge symmetries of those fields, right?
Oh, mhm.
What lives in that exceptional tangent bundle? It's the generators of diffeomorphisms and N forms, P form transformations. So it's
Okay, okay.
incorporating that gauge structure.
Okay, so it's let's say field content also together with saying which fields should be identified.
I mean,
No, I just mean like as you said, gauge symmetry.
oh, I see. Yeah. Okay. Yeah. There's analogous thing. So yeah, as you're saying, dynamics comes in from looking at the generalized metric in ODD, and that comes from that further reduction of the structure group. You can do the same thing for exceptional case, where you can reduce to some maximal compact of those EN groups, and you also get some generalized metric kind of object, which happens, which when you start counting, you'll see that you exactly need those forms and metrics to span out the dimensionality of that homogeneous space, and there will be a they are not necessary, but they are like right parametrization of that homogeneous space upon that extra reduction. So GNB is are the right degrees of freedom to sort of parameterize ODD mod OD times OD, and likewise.
And then the action is just coupling these objects to the coordinates of the string or the brane.
So
yeah, I mean, we say nothing about dynamics of like the M2 brane and M5 brane.
Yeah. And even in string, you can't really couple to RR forms in the RNS formalism. So there's no, the GNB couples naturally, but the R forms, for that you need to go to Green-Schwarz. Green-Schwarz is terrible for other reasons. So yeah, it's even not great over there in string theory.
But you can
sorry, go on, Friedrich.
I mean, you can talk about this target space model, like the supergravity thing, and that one works for strings and for these exceptional things as well. So that you can build some curvature tensors out of this.
Okay, so these are not strings. You only describe the target.
Yes.
I would say that's the low energy effective. You can describe the low energy, like the supergravity limit, the low energy effective action, but not the dynamics of a string moving in some background.
Okay.
But the string, I guess, I mean, Friedrich's right, of course, but I guess knowing supergravity limit, it's not enough, right? Sometimes, like sometimes you need those higher corrections. That's not something you would see from just the supergravity limit, and worldsheet model is useful for that. So I mean, it's another side of the story which can be useful to study sometimes.
But the main issue is that in the exceptional case, we don't really have that side of the story.
Yeah.
Okay.
Yeah.
So with this side of the story, you mean like you don't know what kind of would be a string that couples, like what would be a string that couples to this E?
Right. You can write down a nonlinear sigma model for a string moving in a G and a B field, right? And you can study, like, in principle, that gives you the dynamics there, right? But the question is, okay, well, what's the appropriate thing in the M theory case? Well, we know the supergravity limit, but like, do you write down a membrane model, like sigma model, or like, I'm not quite sure.
Okay. So it's like analog of the Stringfield theory, or I'm slightly confused.
Yeah, Taki.
Okay, but yeah, thank you.
And
also, yeah.
What is the analog of Stringfield theory?
Well, okay, let me maybe say this. So, I mean, I'm not a great understander in this, but so like for string, you have this Polyakov Polyakov, let's say Polyakov model, like the Polyakov sigma model, and there is way to quantize it. And if you quantize it, then you get the quantum theory, and then you can go from there. But for membranes, you can write down some classical things, like some candidates, but there is no known way to quantize them, as far as I understand.
Okay.
That's not really. I don't think that's true, really. I mean, you can go even about quantizing, but it's just there's more complicated things there. Like for instance, for string, you know that every instant of time you can chop off your worldsheet and get just a bunch of circles, and then you associate it to those circles Hilbert space, right? And if you look at the second quantization, you get the Stringfield theory, right? You get all those modes from that circle Hilbert space. But for membrane, you can even quantize somehow. Like it's complicated, but you can do that. Like it's been studied by some people, even though it's way more complicated. But even then, you're screwed, because at instant of time, it's some two-dimensional manifold, and there's way too many of them. And how would you put together all these different Hilbert spaces associated to those different Riemann surfaces at the given instant of time when canonical quantizing M2, for instance, or even and in M5, right? You would have all the different four manifolds in given instant of time. So it would be just, you wouldn't even know how to construct second quantized theory, even if you knew how to do like a easy canonical quantization, say on T2 and T4 for M2 brane and M5 brane. So it's even complicated because of this terrible topological reasons of higher dimensional manifolds, which are the world volumes of branes.
But from what you are saying, it sounds like there is only a technical reason why people are not doing this, like namely that it is hard. But I thought that there was also some conceptual obstacles in there. It was not just like it's hard. It was like we don't know how to do it. That was my feeling.
I mean, this is already something we don't know how to do, right? We don't know what's the Hilbert space, basically. Like what are different manifolds and how to associate Hilbert space to each of them and how to put it together, right?
Okay, but that's what I meant when I said that there is no known quantization.
Okay. Yeah, I guess, but I just wanna. So what I mean, sorry, yeah, I just didn't wanna make an impression that if you take some brane model, you cannot canonically quantize. You can analyze the constraints and you can quantize, but it's just complicated. It's just there's too many degrees of freedom. You can have different time slices, different codimension one manifolds, and too many constraints on it, and we just don't know how to make sense of it all. But I mean, conceptually, I mean, it's just some model with constraints, right? You can do quantization. It's just a mess to put it together in some coherent framework.
Okay. So like in some sense, like just the Fock space construction, it just like it completely fails to capture this four-dimensional topology you told me, or geometry.
So Fock space, so it wouldn't, it wouldn't. I guess in string you're just super lucky because it's just a circle, right? And you can do Fourier transform and you get a bunch of creation annihilation operators. Being on some two manifold of general type for M2 brane, like what would you even do? I guess you have to do some analysis of that. You just have to solve those wave equations on a higher genus surface and just know the full spectrum, which you don't, and so yeah, it's just a mess. I think, but not that like we would probably know how to do all those steps if we I don't know.
That's very interesting. Okay. Maybe I will have one last question. So as you said, that this generalized metric, which you couple to strings or something, this comes from the further reduction to, let's say, OD cross OD in right, and so So to what you reduce in this E case, and like, is this the only option?
Oh, I have a maybe let me share a screen again, because I had this table and there were the compact subgroups for ED. I didn't, yeah. So this last line, it's those compact subgroups you're reducing to.
Maximal compact.
Maximal compact, sorry, thank you. Yes. There's a small caveat maybe. Yeah, I was being sloppy here with the signature. So for instance, in this 40 case, it's not really SO5, it's SO2,3 as it happens. And yeah, there's different signatures because you know, this is just you.
But that one is not compact, right?
That's true, but if you want Lorentzian, you don't really want compact. And
right,
you need to.
here we don't want Lorentzian. Here everything is Euclidean.
Yeah, but then it's not really, yeah. So this is Euclidean picture, but if you really want to do Lorentzian theory, you need those different signatures here. So if you look at the papers of Warren Siegel, he actually meticulously take into account that you have Lorentzian signature, and these groups are not really these groups, but they have some different you know, real form of these groups.
But maybe a stupid question. Why would you want to have Lorentzian things here? Isn't this the kind of what is so this theory is the theory that lives on this torus on which you compactify your space? And that one
you might want to compactify on some Lorentzian.
Okay, I mean, yeah, if you want.
Maybe.
Yeah, there were all these papers at the beginning. So you know, at the beginning of studying the F theory, and they all asked about what should be the proper F theory and its signature up there, such that if you reduce down to supergravity, you get the right Lorentzian, you know, signature, and it turns out that there's actually more time directions in that F theory. So it's kind of weird. There's these papers by Dijkgraaf and Waffa, and it's maybe slightly controversial, and but yeah, it's little strange. I don't think it's fully sort of resolved to this day. But you're right. If you're just compactifying those space-time directions, I guess then you're maybe I was being if you're doing space-time directions, you have these groups, right? If you have some time in it, you need different real forms, such that you get the right signature of the Lorentzian theory down in that 10D or 11D.
Okay. But you said like these are special because they are maximal and maybe compact in some cases.
They're the analog of a Riemannian metric in the usual GLD geometry.
And the maximum one is always unique up to some conjugation or something.
The group is, that's right. There's always a maximal compact subgroup. For these groups, certainly.
There's always the maximal compact. Okay.
I mean, yeah.
Okay, thank you. Okay. Yeah. Thank you very much. I learned a huge amount.
But I think yet that like despite this, there is no like a nice pattern, and it's like there is a nice pattern for these exceptional groups. Like they have this sequence of the Inkin diagrams, but for the maximal compact ones, I don't know if that is like a.
I mean, saying that they're a maximal compact subgroup is already a nice pattern, no? You could pick a random subgroup and that would be bad. This is a maximal compact one.
Okay.
I mean, those diagrams there for like complexified setup, I guess, and then you're just choosing, choosing which dots you're coloring with black and which one with white. If you do all of them,
but I guess the takeaway is that, like, in the same way that when you're doing general relativity, you have this GLD structure, and then your Riemannian metric is a reduction to the maximal compact subgroup. Here we're doing the supergravity picture, and you have some ODD structure, and the geometric data, which is your G and your B field, is parameterized by a reduction of that structure group to its maximal compact. And similarly for the high 11-dimensional supergravity as well. So you kind of encode all of this field content, like the geometric data, in terms of this reduction of the structure group.
Yeah, I'd like to ask about something. Maybe it will be the content of the next lecture, but could you say a bit more about the pairing on in the exceptional case, and how like stuff like isotropic subbundles and that kind of stuff looks like in the exceptional case?
I think, yeah, maybe that's a question for Friedrich. Will you spend time on that next time, or
Yeah, certainly. I like next time we will talk about it. But if you want, I
then
can.
then I'll leave it hanging then, if that's okay, and Friedrich can take over next time. I guess for that it would require some writing, and if he's doing it next time.
Okay, it doesn't seem that there are other questions, so I'm gonna stop the recording here.